darkness. For millions of years after the cosmic microwave background emerged, our universe remained a vast, transparent void. The cosmic dark ages had begun. The searing heat of creation had faded. The primordial fireball had cooled to a mere whisper of microwave radiation. All that remained was an ocean of neutral hydrogen and helium gas, stretching endlessly across the cosmos, gradually cooling as space itself continued to expand. Yet within this seeming tranquility, momentous changes were underway. Gravity, the weakest but most persistent of the fundamental forces, was quietly at work. Those minuscule variations in density, the quantum fluctuations stretched to cosmic scale during inflation, began a slow process of amplification. Regions with slightly more matter exerted slightly stronger gravitational pulls on their surroundings, drawing in more gas, becoming denser still, their gravitational influence growing ever stronger. This process was dramatically accelerated by a mysterious substance we now call dark matter. Unlike the protons, neutrons, and electrons that make up ordinary matter, dark matter doesn't interact with light or other forms of electromagnetic radiation. It makes itself known only through its gravitational effects. And in the early universe, it was already forming a vast cosmic web, a network of filaments and nodes that would serve as the scaffolding upon which the visible universe would eventually be built. Ordinary matter, the hydrogen and helium from which stars and galaxies would form, fell into this invisible framework like water running downhill, collecting in pools at the intersections of dark matter filaments. As these pools grew denser, their temperatures began to rise. Physics tells us that as gas compresses, it heats up. The same principle that warms a bicycle pump as air is compressed inside it. Slowly, over hundreds of millions of years, the first structures recognizable as proto-galaxies began to take shape. These were nothing like the majestic spiral and elliptical galaxies we see today. They were chaotic, formless collections of gas, hundreds of thousands of light years across, still growing, still accumulating matter from their surroundings. Within these embryonic galaxies, the gas continued to fragment and collapse under its own gravity, forming denser and denser clouds. The universe had reached a critical threshold. As these clouds collapsed, their cores heated to thousands of degrees. But this was still not hot enough for the nuclear fusion that powers stars. Something more was needed, a catalyst that could drive temperatures high enough to overcome the electromagnetic repulsion between atomic nuclei. That catalyst would come from an unlikely source, the strangest and most elusive subatomic particle we know. Hydrogen, the most abundant element in the universe, exists primarily as single atoms. But when two hydrogen atoms join to form molecular hydrogen, something remarkable happens. Molecular hydrogen can radiate energy away more efficiently than atomic hydrogen, allowing the gas to cool more rapidly, accelerating the collapse. And another particle, the ghostly neutrino, played its part. By interacting weakly with ordinary matter, neutrinos helped carry away energy, further cooling the densest regions of gas. As temperatures in the cores of these collapsing clouds reached millions of degrees, the first stars began to ignite. These were not the modest stars like our sun. They were monsters, hundreds of times more massive, millions of times brighter. Formed from pristine hydrogen and helium, untainted by heavier elements, these population 3 stars, as astronomers call them, were unlike any that exist in our universe today. Their surfaces blazed at temperatures of 50,000 degrees or more, twice as hot as the hottest stars in our galaxy today. Their cores reached tens of millions of degrees. They emitted primarily ultraviolet light, so intense that a single one of these stellar behemoths could outshine an entire modern galaxy. They lived fast and died young, some surviving only a few million years before exhausting their nuclear fuel, a mere blink of an eye in cosmic terms. The first light had arrived. After hundreds of millions of years of darkness, the universe was illuminated once more. But this new light was different from the cosmic microwave background that had come before. This was the light of nuclear fusion, the same process that powers our sun today. The first stars were cosmic alchemists, transforming the simplest elements into more complex ones through nuclear reactions in their cores. Within these stellar furnaces, hydrogen fused into helium, releasing enormous energy in the process. Then, helium nuclei are combined to form carbon, oxygen, and other elements essential for life as we know it. For the first time in cosmic history, atoms more complex than lithium were being forged. The universe was becoming chemically enriched, setting the stage for future generations of stars, planets, and eventually living organisms. But the first stars were more than creators. They were also agents of cosmic transformation. Their intense ultraviolet radiation began to break apart the neutral hydrogen atoms that filled the space between them, stripping electrons from their nuclei in a process called ionization. Vast bubbles of ionized gas began to form around each star, growing and eventually merging with one another. This process, cosmic reionization, marked another fundamental transition in the history of the universe. Just as the formation of neutral atoms had made the universe transparent to visible light, reionization made it transparent to ultraviolet radiation. A new era of cosmic transparency had begun. The universe was changing again, influenced now not just by the inexorable pull of gravity, but by the transformative power of starlight. The most massive first stars lived brief, spectacular lives. With masses hundreds of times that of our sun, their cores quickly exhausted their hydrogen fuel and began fusing heavier elements at an accelerated pace. When fusion reached iron, the most stable atomic nucleus, the process could no longer release energy. Without the outward pressure from fusion to counterbalance gravity, the stellar cores collapsed catastrophically. The result was the most energetic explosions the universe had yet seen, the first supernovae. In its final moments, a dying massive star would outshine all the other stars in its protogalaxy combined. The energy released was almost beyond comprehension. In a few seconds, a supernova could radiate more energy than our sun will produce in its entire 10 billion-year lifetime. These cosmic detonations had profound consequences. The explosions scattered the heavy elements forged in the star's cores across space, seeding their surroundings with carbon, oxygen, silicon, and iron, the building blocks of rocky planets. Some supernovae left behind exotic remnants, neutron stars, where matter is crushed so densely that a teaspoonful would weigh billions of tons on Earth. Or black holes, regions where gravity is so intense that not even light can escape. Unlike their massive forebears, some of these stars were small enough to still be shining today, nearly 13 billion years later. The oldest stars we can observe in our own galaxy, ancient red dwarfs in the galactic halo, are these population 2 stars, born when the universe was less than 1 billion years old. They are cosmic fossils, preserving in their atmospheres a record of the chemical composition of the early universe. As the first protogalaxies continued to grow and merge with one another, larger structures began to form. The cosmic web became more pronounced, with massive filaments of dark matter channeling ordinary matter into growing nodes. Gas following these cosmic highways fueled star formation in the nascent galaxies, which grew more luminous with each new generation of stars. These first black holes, though modest by today's standards, would play a crucial role in cosmic evolution. Some would grow to become supermassive black holes that anchor the centers of galaxies. Others would merge in cataclysmic events that send ripples, gravitational waves, through the fabric of space-time itself. Even today, our most advanced observatories can detect these cosmic tremors from black hole mergers billions of light years away and billions of years in the past. With each supernova explosion, the interstellar medium became progressively enriched with heavy elements. The second generation of stars formed from gas that contained traces of these elements, making them slightly different from their predecessors. These population 2 stars, as astronomers classify them, could form with lower masses due to more efficient cooling facilitated by the presence of heavy elements. These early galaxies bore little resemblance to the majestic spirals and stately ellipticals we see today. They were chaotic, irregular assemblages of stars and gas, often in the process of colliding and merging with their neighbors. Star formation occurred in furious bursts, rather than at the steady pace seen in modern galaxies like our Milky Way. The early universe was a place of cosmic violence and spectacular creativity. As ionization progressed, the intergalactic medium, the vast spaces between galaxies, became increasingly transparent. Ultraviolet light from galaxies could travel freely across the cosmos. The Dark Ages had conclusively ended, replaced by a universe filled with the light of countless stars, organized into thousands, then millions, then billions of galaxies. By the time the universe was 1 billion years old, less than a tenth of its current age, this transformation was largely complete. The fundamental architecture of the cosmos had been established. From quantum fluctuations in the earliest moments after the Big Bang had grown a cosmic web of dark matter. Within this web, galaxies had formed, populated by generations of stars that created the chemical elements necessary for planets and life. The stage was now set for the next chapter in cosmic evolution. In the coming billions of years, galaxies would grow and mature. Planetary systems would form around countless stars. And on at least one small rocky world orbiting an unremarkable star in an ordinary spiral galaxy, the elements forged in ancient stellar furnaces would combine to form life. But that is a story for another time. For now, we marvel at the journey from darkness to light, from simplicity to complexity, from the first moments of creation to the dawn of a universe recognizable as the ancestor of our own. In just 1 billion years, the cosmos had transformed from a featureless sea of hydrogen and helium into a vast cosmic ecosystem of stars and galaxies, the foundation upon which all future cosmic evolution would build. The story of Before Earth has only just begun. If you enjoyed this episode, make sure to hit that subscribe button and turn on the notification bell so you don't miss the next episode. Also, leave a comment with at least 8 words. Your feedback helps us grow the channel and create even better content for you. Thanks for watching, and we'll see you in the next episode.